Good evening, ladies and gentlemen. Great pleasure to talk here. I think about a topic that's very dear to my heart, namely the value of basic science, the fundamental sciences. And I'm very much aware I'm doing this at quite a momentous time for Ireland. So, where everyday worries are taking over, but I will actually want to talk about the long term, past and future, and how we kind of organize looking further than we can possibly oversee at the short term. In fact, another title I thought about was this. Actually in Dutch it's one word, grenzen van de wetenschap, but in English it's three. The frontiers, the borders and the limits of science. What can science do and cannot do? And I want to also explain a little bit this image that you've seen on the poster and on the folder. It's actually a drawing I made in my PhD thesis. And it's a variation on a rather famous drawing by Dürer, an etching, called Melancholia 1. And that actually, this one is asking for a second copy. And I will actually, if you look very carefully, you see that various ingredients of this famous drawing of Dürer, which in some sense is symbolizing, I would say, kind of it's kind of a moody image, but it's reflecting, I would say, the deeper thoughts that the arts and the sciences have. And you see the angel is surrounded with various kind of figures and instruments. And I've kind of an updated version where the instruments and ingredients of modern science play a role. I will illustrate a few of them during my lecture. Let me come back to the title, On the Other Side of the Hill. It is actually taken from a quote. Somebody who was born in Ireland. I'm not actually sure I can actually quote him here legitimately. Arthur Wellesley, the first Duke of Wellington, the Iron Duke. And he had this famous quote that all the business of war, and indeed all the business of life, is to endeavor to find out what you don't know by what you do. That's what I called guessing what's on the other side of the hill. Now you do know that he was called the Iron Duke, not because of his fierce action in battle, but because he was very unpopular as the Prime Minister of England and had to put iron railings for his house in order to protect against the angry crowds. But when he was retired, he had the habit of taking some friends in a coach to some space, some territory he didn't know, go to the top of a hill, and then look at the landscape, and the game was to predict what is the land behind the next hill. And then they would go with the carriage and actually find out who was right. And he was often right. So he had kind of a very good kind of intuition. What were the things hidden from sight, but which were there far away? And this vision, I would say, it's kind of tunnel vision, but in a positive side, to see what you don't know and build ideas upon that. I think that's a fundamental quality of science, which I would say is extremely valuable to society, but it's very difficult to capture. And I want, with some anecdotes and some stories, kind of try to bring this point in front, looking through the hill tonight with you. This experience of actually going through this transition, I would say going through the tunnel, was very well phrased by Richard Feynman, the famous particle physicist. And he put it here very well. If you read the quote, you see that in some sense, your life is simple, and certainly it becomes more complicated. There are facts, little things that don't fit in the picture that you have in your mind. And it's get more and more complicated, and suddenly everything fits together again, but in a bigger scheme of things. And when you're finally through this very confusing period, you have a different take on this phenomena, different view on the scientific theory that actually explains more and in a deeper way. And this process we try to go through in research now and often. It's like this visual illusion. You can look at this picture, you see this very famous one. You either see a young girl or an old woman, but you see it's very difficult to see two at the same time. So in your mind you have either one image or another image, and certainly it kind of flips around. So this is kind of a famous thing. One of my favorite stories about the birth of quantum mechanics is you all know that in quantum mechanics you have this complementarity phenomena that like an electron can be both a particle and a wave. And when it was first discovered by Heisenberg, he wrote about this to his dear friend Pauli. And Pauli writes back, I think 1 week after discovery, he has a beautiful quote. He says, well, it's like if I look with one eye, I see the particle, and if I look with my other eye, I see a wave, and if I open both eyes, I become crazy. So I feel, even referring to the political situation, perhaps you feel a little bit like this, you know, very much uncertain. But of course the wonderful thing is that in science we have this kind of luxury of going through these kind of transitions. By the way, Pauli was a very strong critic of himself and of others. And there's another postcard he wrote to Heisenberg in later life. Heisenberg had given a wonderful theory about the universe and everything, but he wasn't very specific. And then Pauli sent back a postcard. He just drew this empty square. And he said, this is to show that I can paint like Titian. More details will follow later. Another kind of, I would say, kind of a metaphoric moment. So this is one of these famous heroic depictions. This is Herschel, Wilhelm Herschel, doing an experiment, a famous experiment. So he is projecting with a prisma, basically the rainbow. He's measuring the temperature of light. So he first measured the temperature of the blue light, gets a certain temperature, then he measures the red light, it gets warmer, and then he does something that only I would say a genius or a crazy person will do. He measures next to the rainbow that's even warmer. So this is the discovery of infrared light. So it's actually beautiful that it's kind of painted without showing it. And of course this I think is a very good metaphor. The little thing that we see, the visual image, of course now we know it's electromagnetic spectrum and stretches all the way from the long radio waves to the very high X-ray waves. Another example, equally famous, these are Penzias and Wilson, discovery, the famous discovery of the cosmic background radiation. You know, they had this microwave telescope, there was kind of a buzz, a noise in it, they couldn't remove it, and turned out they were actually listening to the very earliest signals coming after the Big Bang. So there's this kind of famous pictures we have now of this noise, this kind of baby picture of the universe. And I don't know if you've seen it, but actually the sign, so if you look very carefully, you see the initials SH. So Stephen Hawking claims that he painted this. And it's again something, you know, once you have seen it, you cannot unsee it anymore. Whenever I see this painting, I see the initials. But why I'm showing this picture, because I think that's another metaphor I want to use, is that by making these very careful measurements in cosmology, and you have heard about this figure, we know exactly in cosmology what we don't know. If you look, all the matter that's missing, the dark matter, all the energy is missing, the dark energy, they account for 96% of the energy content of the universe. Only 4% is known. And I think this is something that we can try to apply to other fields. So I would say I'd like to call this kind of dark knowledge, things that you know, you don't know. So physicists can claim that they don't know 96%, and I ask people in other fields, what's your percentage of dark knowledge? For instance, you can ask people who study ancient Greek text, and I think they're roughly 3 to 4% of the texts that were known at these have survived. So they know that they don't know. If you talk to somebody studying fossils, it's very difficult to get an exact number, but I think 1 in 10,000 or 1 in 100,000 of species that have lived have left even only one fossil. So you are confronted with this enormous body of knowledge that you don't know. And I like to depict kind of the things that these scientists are doing, like these old cartographers who were drawing pieces of the map, but of course they were kind of afraid of nothing. So the pieces that didn't know, they always put these big sea monsters there. And I think in some sense that's the dark knowledge, and that's the knowledge that we try to kind of to see and understand. And in some sense I think here is where the scientists are in this little boat here in the big seas. In fact, there's another kind of knowledge that you don't even know that you know it. It's this famous quote by Donald Rumsfeld, who was of course the defense secretary at the time of the Iraq War. And he had this press conference and he was making this philosophical point. There are things you know, the things that you know you don't know, and then there's the third category, the unknown unknowns. And I think, of course, this was a kind of a very good example of unknowns. It was a great tragedy. But I think he was making a good point, and I would like to put another quotation here, which is by Francis Crick, the co-discoverer of DNA, a theory that can account for all the facts is wrong because always some of the facts are wrong. So I think this is such an important thing of science, that we are always aware of these unknown unknowns. And in fact, this is particularly true for, I would say, fundamental basic ideas. And I want to illustrate it with a few examples of my own field, kind of mathematical physics. Now, there's a famous paper written, some of you might know it, certainly might know the title, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. It's a famous paper by the mathematical physicist Eugene Wigner. And he starts his paper with an anecdote. And this is an anecdote that's been told in many different ways. I like to tell it in the following fashion. A mathematician meets a shoe salesman. And the owner of the shoe shop is complaining that he doesn't know to have how many shoes in which size. And then the mathematician, oh, it's very easy, you know, there's a statistical distribution explaining this. And he shows this graph and he shows this formula. And then the mathematician says, what's this funny symbol there on the right-hand side? You know, well, it's the Greek letter pi. Well, what's that? Well, it's actually the ratio of the circumference and diameter of a circle. And then the shoe salesman says, what do circles have to do with shoes? And Wigner makes a point that's rather amazing, that this geometrical feature, the ratio of the circumference to the diameter, is actually appearing in this statistical model. So clearly this notion of the Greek, the symbol pi, the mathematical symbol pi, is extremely powerful. And indeed, whenever you make a computation, you find a sine and a cosine in a certain problem, you have to ask, where is the circle? The circle is somewhere. So mathematics has this wonderful property to pop up very unexpectedly, unreasonably effective. I actually want to illustrate it with a famous kind of Irish example, the quaternions, Hamilton's solution. And I think we should mention it here, and of course we're celebrating 70 years of Dias, that I'm personally very much touched that the founder, de Valera, actually wrote down these formulas also when he was in a prison cell. It's very rare to have a country where somebody that famous and that politically influential in this very painful moment writes down a mathematical formula. I think you are very proud of this, but you should. And if you want to see what is the concept of the quaternions, I would say in the modern way, you would say it really has to do with rotations, with symmetries of three-dimensional space. And I want to illustrate it with one element I picked out on my version of melancholia, which is this so-called Platonic solid that I pictured here on the left. So this is a kind of a nice story. You know, the Platonic solids, the 5 regular solids, purely symmetrical objects, very well known to the Greeks, and at that time, high point of mathematical culture. And they had various arguments for it. One argument was that the 5 solids had to do with the 4 elements. In fact, the 4 elements, they had a good logic to it, like the cube was earth, because you could build something of it. The tetrahedron was fire, because sharp angles, you could hurt yourself. And of course, the problem was with the middle figure, the dodecahedron. And Plato actually says, he actually puts in the text like a suggestion that this might be the material out of which the rest of the cosmos is made out of. The things outside Earth. And actually, typically what happens to a theoretician, next generation Aristotle says, well, this actually is part of the theory, but it was only a suggestion. And so this is the 5th element, the quintessence. And if you go through, for instance, the history of art, you see many depictions of the dodecahedron because it's kind of it's the magical element, it's the metaphysical element, it's the cosmological object. And so it's really something which is very fun in mathematical circles. Somebody once told me, well, he liked the object because it's complicated but not too complicated, which I guess is a good definition of mathematical elegance. And you see it everywhere. For instance, here there's a famous painting of a monk, Luca Pacioli, who was usually celebrated as the inventor of accountancy. So very down to earth, register is honored. But actually this little symbol there is actually indicating that in some sense, it's not only the books he's interested in, it's also kind of this metaphysical aspect that he is cherishing. And even in modern art, and there was a kind of a brief moment in history of science when actually it appeared on the cover of Nature, because at that time cosmological observations were suggesting that actually the universe itself has the shape of a dodecahedron. So that's kind of this Platonic resonance was of course not missed. But now we know it's not that. But I want to actually come back to these regular solids because in the form of Kepler. And this is often given as an example how not to apply fundamental ideas. So Kepler, as a young scientist, was really in love with these regular solids. And his first book, he was 25, was his cosmology. He applied actually this mathematical theory to the universe. And the universe in his case were the 6 planets orbiting the sun. So he thought 6 planets, well, I have 5 regular solids. So that actually fits very well, because if I fit the 5 solids into each other, and I can do that in 120 possible ways, he found one where the relative ratio of the size of the spheres actually matched within 5% the ratios of the orbits of the planets. So this was his cosmology, and often it's kind of made jokes about because there are many, many arguments why this isn't right. But I tell the story because actually it was Kepler himself who kind of destroyed this model. And he did so by measurements. So of course all know Kepler's first law is that the planets are moving not on circles but ellipses. And he writes, when he noticed this by careful observation, he writes in his diary that he felt he carried a horse cart of manure into science. That's how it's often put. Because the perfect shape of the circle was destroyed. And well, it's this ellipse, but it comes in all kind of sizes, so it's kind of an ugly thing. So the world outside the Earth was no longer perfect. But actually the full quote of Kepler is that he brings a horse cart of manure into science to remove an even bigger horse cart of manure and kind of tidy up the theory of the universe. So in some sense, he actually saw it a very positive way. And in the modern framework, you would say, well, wait a moment, these laws, the laws of the orbits of the planets, Newton's laws, their most elegant mathematical solution does involve symmetries. Not the symmetries in 3 dimensions, even symmetries in 4 dimensions. It's rotation group SO4. So he was right, but not in the details. In some sense, he was looking for a mathematical structure, but he should think more in universal mathematical structures, dynamical systems, symmetries, and not in the exceptional nature of this one regular solid. Now, there's kind of nice tale to it, because now we know that these figures that he projected in the heavens, they were just around us. Now, if little pieces of soot have molecules, buckyballs, which have exactly this shape. In fact, these days you can just find microscopes that actually literally take pictures of these objects. So I think that's also kind of nice, that he was probably thinking and writing a little candle which root was coming off, where actually these molecules were just there. In fact, if you carry this on, now we know this is a very hot topic. This year's Nobel Prize was given for graphene, which is some version of the same material, not rolled up into a ball or rolled up into a cylinder, nanotubes, with one-dimensional or two-dimensional layers of this material. So his idea of looking at the symmetry was extremely powerful. In fact, this 6-fold symmetry was very much to his mind. There was a famous book Kepler wrote. He gave actually to Rudolf II, his Maecenas. He wrote later, and it's actually on a snowflake. It's a famous kind of gift, Christmas gift, that Kepler made. And, you know, I want to mention this book because he actually, in this discussion about 6-fold symmetry and about the snowflakes, he actually discusses a practical problem. You might have heard of Kepler's conjecture, what's the best and most economic way to make a pile of cannonballs. It's a famous problem that was only solved a few years ago, 400 years history. But I mention this because there is actually, if you want to have this the theory of lattices and how to tightly pack spheres, there's a mathematical word that's used that I like very much, which is indicates the number of spheres one sphere in the lattice touches, and it's called the kissing number of the sphere. So I would say these kind of fundamental ideas have a very high kissing number. They touch many, many different areas, I think it's wonderful that there are objects like that we can study. So the quaternions, I think, is a very good example of this. And actually, I can carry this further forward. But look at the other corner of my drawing. You find something which indicates it's a magical square. With Dürer, here it's actually a magical square of particle physics. So if you look at modern particle physics, studying these experiments, the idea that there is a mathematical theory behind this is something that is actually not at all obvious. In fact, there were periods in the history of particle physics in the 1950s and 1960s when people were contemplating what's basically called S-matrix theory, of this black box approach to particle physics. At that moment, the theory was there is no theory. The particles go in, particles come out, and you can study correlations. But there is no fundamental descriptions of the law of nature. Some said that was the fundamental law. And in fact, these days, I would say people in particle physics are really desperate to make contact with mathematics. And there's this famous quote of Freeman Dyson, famous mathematical physicist, that the marriage between mathematics and physics had ended in divorce. Kind of a hopeless state of mind. But the interesting thing is that he made this remark exactly at the time when this marriage was kind of blossoming again. Because this was the time that particle physics, all the great discoveries were done, and actually it turned out to be a beautiful mathematical theory underlying it. So I would like to say that in this black box there's a kind of formula. So if you use very elegant notation, you can write a formula of the standard model. And the amazing thing is you can give a lecture to mathematicians about this formula. To mathematicians who doesn't know a word about physics, but they recognize all the symbols. All the symbols are entirely geometrical, they're entirely logical. It's beautiful mathematics, really underlying the fundamental nature that we see around us. Of course, it's not the way the formula is taught in the, say, graduate class. You get something like this. That's how I was taught. And clearly, you know, this is by Tini Veldman, who got together with Geert het Hoofd got the Nobel Prize, and he liked it to scare our students. But of course, at the same time, you can say, well, the same model, it would kind of fits on a t-shirt. It's rather amazing that we have this ability to really describe all of nature around us with these very elegant and reasonably effective mathematical means. And if you see what is at heart at the standard model, I would say it's still symmetry. So Kepler was in some sense entirely right that this is the way to understand physics. In fact, if you think about forces of nature, the modern way to think about this is in terms of symmetry acting on particles. So for instance, a quark, an elementary constituent of matter, comes in 3 different colors, so to say. So you can think of it as a little, please admire my homemade PowerPoint animations. You can think of it as a little vector, a little arrow pointing in 3-dimensional space. And this arrow is basically everywhere in space-time, so it's like this. So I would like to call this the communist model of particle physics, which is very much not how nature is. So it's more like the Dutch way of everybody is free to orient himself in this space as you want. But it's kind of beautiful that this symmetry in this way, if you would say the waves in these little arrows, are the modern way in which we understand the forces that hold matter together. So it all turns around this one mathematical object, extremely powerful. But starting with the old Greeks, it's a period of more than 2,500 years. Now, one aspect of this, as I was claiming, is that you have to deal with the unforeseen applications of science. And also you have to deal with the uncertainties that are always part and parcel of how science operates. And I will say in the end of my lecture something about the climate science. But clearly that's typically a case where we are in an extremely powerful way confronted with, we say, the innate errors, uncertainties that are in science. And when we were given this, given the task, I'm also chairing a union of academies, worldwide union, when we were asked by the Secretary General of the United Nations to review this climate panel IPCC, there was only one question that was asked of me by any reporter was, well, will there be a skeptic on your panel? And I must say my prepared answer was, every good scientist is a skeptic. Which is, I would say, a little bit slick, but it's true. In fact, that's something that, of course, you always are up to this. And I like this quote again, if I can bother you with another quote of Richard Feynman. Science is the belief in the ignorance of experts. So it's very important that in science we emphasize it's the facts that speak. And as he said here in a very Feynman-esque way, when a scientist doesn't know the answer to a problem, he's ignorant. When he has a hunch as to what the result is, he's uncertain. And when he's pretty darn sure of what the result is going to be, he is in some doubt. You always keep doubting. And the thing is that the public has to trust us. That it's not our status, it's not our consensus, but it's the facts in the end which have the last word. I like this other quote of Bob May, former president of the Royal Society: science is organized skepticism. Of course, that's an extremely important property that we have to keep. And that's why in the scientific community we always have debate. We're not operating according to consensus. We are debating on discussion and facts. So perhaps you have seen this famous example that happened last year. Just to give you a little anecdote in between, there was this newspaper described a woman making cake and picking 6 eggs in a carton. All 6 were double yolks. And then there was a big discussion about, what is the likelihood of this happening? And the calculation was there's a chance in 1 in 1,000 that an egg has a double yolk. So you can easily see it's a chance of 1,000,000 times 1,000,000 times 1,000,000 that this would happen. So you really have to bake a lot of cakes for this to happen. And you can see this is actually completely unlikely. And then there were many experts who moved into the debate. For instance, modern chicken, they are fed, various hormones, so they might produce more yolks, and perhaps the one chicken is responsible for all 6 eggs, and suddenly the number went down, but it's still rather astronomical size. And then suddenly one of the experts walked into the supermarket and he saw cartons, double yolk eggs. And this explained the phenomena. So I think that was kind of one of the unknown unknowns. And as a scientist, you always have to be aware of this thing happening. And again, give you an example, which I would say would be the climate problem in the 19th century, which was at that time the stability of the solar system. So it's a very important question asked in astronomy. Even if you know the laws, or the planets are circling, what is the chance that someday one of the planets get ejected out of the solar system? So it would be very, very upsetting if we wake up and the sun was nowhere there, we were in intergalactic space. And of course this dates back to the famous astronomer Laplace. Laplace developed the whole theory of celestial mechanics, and of course he had this uber-deterministic image of science that if there would be a being, all-powerful being, knowing everything at one moment, science would predict the future. And I think that, in some sense, is still something that kind of hangs to us, this vision of really predicting the future. Now, of course, the story is that there was, most of you are familiar, I guess, with it, that there was a competition in the 19th century, mid-19th century, by the Swedish king to prove once and for all the stability of the solar system. There was a young French mathematician, Henri Poincaré, who put in this submission, and suddenly kind of woke up and thought, my God, I made a mistake. And I would say he phoned up, but of course he couldn't. He wrote to the Swedish Academy and said, well, I want to retract my submission because I made a mistake. And he got an answer back, it's too late, you already won the competition. And so was this the end of his career? Of course, no, it wasn't, because what he discovered, and that's where he became very famous of, is that there are special conditions under which the solar system indeed is non-stable. And I think, I'm not an astronomer, but astronomers tell me that's quite likely that in the several billions of years of existence of the solar system, one planet was ejected. And the solar system is, so to say, chaotic. Very small differences make enormous effects. So this is another amazing property, I think, of science, that in some sense a kind of victory in defeat. When people are disappointed, they prove something wrong, actually it's usually the birth of a new field. When Gödel proves that basically undecidable mathematical theorems, it wasn't the end of logic, it was really the beginning, the blossoming of mathematical logic. And there are many examples of that. In mathematics, in physics, in the other fields. And actually that brings me to, I would say, you see us slowly moving away from the basic science, but to the innovation aspect. And here I kind of highlighted the cat. Now I must say that I put the cat in the Melancholia 2 as a reference to Schrödinger. It's Schrödinger's cat, but it's also my cat at that moment. And my cat had a certain property, so I like to kind of put him on my lap, but he didn't like that. So he would be fighting, you know, to leave my lap. But at some point, I could remove my hands, and the cat was still fighting an invisible hand. I always felt it was a very good metaphor of how the human mind works. You know? There's an invisible hand stopping us thinking new ideas, say, inventing new things. It's something I think is lack of imagination more than kind of that there's not enough space in our I would say in theory space, in possible ideas and concepts. And of course that you can see very well by not looking in the future but looking in the past. And it's interesting if you go like 50 years back and you look how people envisioned that we would live in 2010, some things were right and other things were wrong. I think often you see people kind of floating in flying saucers, you know, and of course when you're in a traffic jam and you're contemplating these images, you think that's really, how could be so wrong? Because the amazing thing is that you are in the traffic jam and you're kind of phoning your friend in the US or something, and you're actually making contact, you know, you're going much faster in communicating than actually you could possibly do with any rocket or something. So there are clearly great phenomena that were not properly foreseen. I remember listening to somebody, I think I was in high school, somebody was very enthusiastically talking on the radio. He had the vision, at some point everybody could be reached by phone. And his vision was the following, that in every room there would be a telephone, and if you walked in, that would be a very smart telephone. It would recognize that you walked in the room, so that the moment somebody had to call you, that particular telephone would go off. Which I think is a beautiful wrong idea, right? So not the mobile phone, but every room a phone. Could also give every person a phone. Very difficult to make these kind of predictions. I like this cartoon of the New Yorker. The wheel is invented, fire is invented, what's left for us? And we really have to kind of think of this. And I mean, I'm not at all an expert in technology, but I must say I appreciated this definition of technology I saw the other day, that it's everything discovered after you were born and everything that doesn't work. I think it's very good, because there are many things that do work and were already when you were born that would say there are technology, but you wouldn't consider, nobody I think here in the room would consider radio to be technology. But more important, it's an enormous force that shapes and changes nature and culture. And it's interesting that if you learn about history, you learn many facts and things, but often, I see this with my own children, when they are taught history, nobody tells them that the last 200-300 years, life expectancy, certainly in Europe, tripled. And of course it did by science. So I like to call science kind of the silent force of history. But in some sense, you know, it's going so slowly, but it's so pervasive that we kind of think it's always there, and we take this for granted. But of course it has been shaping human lives in a way that's very difficult, I think, to imagine. But it almost happens not at geological scales, but it does happen at scales which are very difficult, I think, for us human beings to fathom. I think that's one of the points I'm talking about tonight. How can we organize ourselves in such a way that we see this long-term perspective? And science is key to this. And science, of course, well, it's moving in a very complicated space, and certainly I'm very much aware this debate has been raging and is still here in Ireland. I would say it's certainly a three-dimensional space, at least. Certainly there's the excellence of science itself, there's the economic relevance to it, And then I think there's a societal relevance, what it actually does for society. And moving in this three-dimensional space is very difficult. I think people often take a certain perspective and see only one of the three axes. And I think that this is something that we are struggling with. I mean, one thing, if we want to present science, we have to present that both the internal quality and I would say the external relevance are there, but they go together. And particularly, I think when innovation and research are brought together, this is famous kind of triangle, but I think it's kind of an impossible triangle in many ways. It's very difficult to have innovation, research, and education come together in a really constructive way. And I think this is something that I'm personally very worried about, is how because connecting basic science to innovation and development is one of the topics I want to talk about tonight. How do we bridge this gap between science and society? And here I think there are two models that are really fundamentally different. And I have a very strong preference of one of the two. One is that if you want to bridge that, you build lots of intermediate structures. So you separate fundamental science from the slightly less fundamental to the applied, to the more applied, and you build separate institutions. You make the big gap into many, many small gaps that people can jump over. There's another model that I feel is much more in line with the historical strength of research, is that you really build a big bridge using the natural tension there are in the sciences. So I do feel that both the fundamental and the applied aspect really go together. And any division of the two doesn't make sense at all. This is sometimes a problem because there are areas, I would say, that really have difficulty arguing for their applications, but I must say there's also, and many people who study like mathematics or something feel very close to that. But there's a mirror phenomena that people who are in very applied fields, for instance in information technology, computer science, they have to argue that there are fundamental basic questions in their field. In fact, there are issues in computer science which are as deep as they are, and they're related to fundamental aspects of logic, that are as deep as they are, for instance, in number theory. And so you can also be the curse of have an application. And there's this famous, of course, saying by the number theorist G.H. Hardy that he felt that he was doing number theory because it was devoid of any application. And these days, of course, number theory is very much applied in coding theory. And one of my colleagues in the Netherlands, Hendrik Lenstra, is a famous number theorist. He once gave a lecture and said, well, of course, these applications are there because the number problem is so difficult that you can't solve it, so that's why it's a good code. He said, I want to crack that number theoretical problem because I want to liberate my field, number theory, the queen of mathematics, from its applications. Of course, it was a joke. But I think actually, I want to end on a serious point. So we very much aware, as I say, even tonight, of the economic crisis raging. But there are, I think, other crises that we have to worry about. When there is an ecological crisis, how do we deal with our planet in a really sustainable way? But I would say even behind that, there's a third crisis that I want to end with, which I would like to call the knowledge crisis. Because I think we really have to worry about how science, how education, how the whole organization of knowledge is taken care of. Because I think that, in the end, it's important because that will be the ingredient that could prevent or solve the other crises that I mentioned. And I think here we really have to do some hard thinking about the nature of scientific research itself. So one thing I think that we have been very active, we're like a hyperactive butcher who took science and divided it in all kinds of bits and pieces, while forgetting that there is a natural unity to science. Well, this is kind of famous saying that the world has problems and the university has departments, but there is an issue to that. And I think that is in some sense something that we are worried. I mean, it's a paradox. The paradox is that we are more and more specialized by nature because we have to go very deep to understand. It's like digging a mine deeper and deeper and deeper to bringing these very deep thoughts. that take a long, long, long time line of research. But of course the amazing thing is, because of these very fundamental breakthroughs, we have applications that are touching us in all possible ways. Instead of having a computer as big as this room, you have one in your pocket. You can have personalized medicine because we really understand your genetic makeup. So I would say science is both infinitely far away at some point and infinitesimally close by. So I think we have to come to grips to that. And only thinking to subdivision actually is not working. In fact, this kind of specialization, I feel, is a risk. So at the same time, we have to kind of hang together. I think not only in terms of the various disciplines, but the point I'm making today, also being kind of generous from both the basic and the applied side. And I would like to say, and this is, I think, very relevant to the nature of the institution that we're celebrating here tonight, the Dublin Institute of Advanced Study, second institute of advanced study in the world, after Princeton, that in some sense the biodiversity of the scientific effort we have to keep intact. We are worried about having biodiversity in the Amazon jungle, but we have to do the same for scientific efforts. And we do know there's kind of a, here again I have my Gaussian distribution, there's this long tail of rare phenomena with enormous impact. And if you get the tail wrong, you're really influencing history in a very dramatic way. So that means that in this wide spectrum of forms of research, there should be a place to have, think 10 years, 20 years, 50 years ahead. Because that's, I think, part of what science is. And in fact, many of the real breakthrough events we know happen from people who were in this very long tail. Both in terms of choice of topic, and I would say also perhaps in the makeup of their intellect, being in some sense orthogonal to everybody else, which makes them extremely valuable. And I think the same holds for institutions. I think for DIAS is really an example of a small institution, kind of a rare bird, which is extremely valuable, but we have to protect it. And as I said, it has to do also with the nature of the interactions of science and society. I think if you go back 100 or 200 years, in some sense there was a good, clear demarcation of where the science is and where society is. But exactly because of the effect I described. This fact that science becomes smaller and smaller and smaller, it's kind of invisible, at the same time it infiltrates everything. I feel the interface between science and society is no longer a straight line, it's basically like a fractal. It's everywhere. And this is completely, I think, influencing and changing the way, certainly from the point of view of a scientist, how we are behaving in society. It actually makes our life very complicated. And that's the final thing I want to address is, how do we deal with these issues? And I think the case of climate science, which is the issue I mentioned before, is a very good case and study. As you know, last year we have seen enormous political pressure on, I would say, the poor scientists who were in that field. And if you look at the reports they have written, so I mentioned this IPCC report, it's actually 4 reports, each 1,000 pages long. So if you stack them together, you have 4,000 pages of facts. And I think there have been a handful of mistakes found there. And the effect was enormous. It's in the culture, it changed dramatically. And of course, incidents like a big snowstorm or a big hurricane changed the public perception in a very dramatic way. And in some sense, it's almost like you build, I would say it's like the Titanic, and you have a little hole, but of course if there are no kind of walls, if there are no compartments, if the internal structure of science is not well organized, in the end it will sink to the bottom of the sea. So science becomes, at the same sense, very vulnerable. And that means that we have, to some sense, I think, the lesson I learned from that is that the internal organization of science and the way we organize our research, the way we train our students, the way we train scientists themselves become absolutely crucial for science to keep playing the role it has been playing in society. And you should, it's not every area I think is under such pressure, but we have a a long history of scientific fields being viciously attacked. So there's this famous example of the fight against smoking, essentially. You know, there's this famous quote, "Doubt is our business," where the tobacco lobby said, well, no, we can't do anything of the scientific facts. They're basically right, but we can create doubt in the minds of people. And so I think as scientists, we really have an obligation to defend science, to make research in such a way that actually in the end the facts can speak. Now, I think if you take these lessons, you see that actually, because we're talking about the value of basic research, and I'll tell you a final anecdote. My own field is particle physics, and last week I had to debate one of my colleagues who's doing laser optics about the value of and we did this under the title "The Last Accelerator," because he felt, you know, they become so expensive at the end of it. And we were supposed to have a very strong debate, but it didn't happen. Because in the end, my colleague said, you know, well, I'm in a different field, but I know that all the students come to the university because they want to think about black holes, they want to think, and I'm so lucky you are there. But once they enter the physics department, they start to think about other things, and at some point, you know, it's all one family. So people in the audience were disappointed they didn't have a very intense debate. But I think he made a very good point. Because I think in the end, if you look at what is the output that science is making, what universities are making, I think in the end it's not a product, it's not the medicines, it's not the technology, but the greatest product that we produce is the highly trained young people who will have a career everywhere. And I think and they go, and in fact they go on for years and years and years. And in fact, they train the next generation, they train the next generation. So that's in some sense, I think, the way we have been organizing this long history of science. I think we need to strengthen it. My final message is that we have to keep this ability to look what's on the other side of the hill. Of course, I don't know what's on the other side of the hill for Dias, but I think we can say that it has 70 years of extremely successful scientific effort, creating, I think, an ecosystem that's absolutely rare in the world and very much needed. So a happy 7th anniversary. Thank you very much.